Hello everyone, and thank you for joining today's webinar. My name is Reese and I'm going to be your moderator today. We're going to kick off today's session in a couple of minutes. We're just waiting so everyone has a chance to join. In the meanwhile though, we'd love to hear from you. So let us know where you're joining from using the chat or the comments, depending on where you're watching from. And yeah, maybe tell us something that you'd like to get out of today's webinar. We're going to be using DagsHub for the code along today. So sign up for an account. I've put a link in the chat. So please go find that. I will also be reposting it for anyone that's missed it. And we'll also be using Google Colab today. So if you don't have Google Colab, get signed up for that as well. But again, I will be posting links to these again. I'll be back to repeat these messages for any new joiners shortly. But until then, enjoy the background music. Hello everyone, and thank you for joining today's webinar. My name is Reese and I'm going to be your moderator today. We're going to kick off today's session in a couple of minutes. We're just waiting so everyone has a chance to join. In the meanwhile though, let us know where you're joining from and yeah, tell us something that you're looking to learn in today's webinar. Just a note, we are using DagsHub today, so please sign up for an account there, and we'll also be using Google Colab as well. So if you haven't got access to those tools, please get them sorted now. I will be posting links to them in the chat and the comments shortly. I'll see you again shortly. Hello everyone, and thank you for joining today's webinar. My name is Reese and I'll be your moderator for today's session. We've just been waiting so everyone has had a chance to join. So nice to see that everybody is joining from a variety of locations, lots of people from lots of different locations today. Quick note from me before we get started, we're going to be using DagsHub today as well as Google Colab. I posted links to those in the chat, so get signed up to both of those before we get started so that we can all code along together. Brilliant. I think that's about it from me today. So I'll hand you over to your host for today's session, Richie. Richie, please take it away.
Hi everyone, this is Richie. Thank you for joining us. As Reece said, it's really amazing to see everyone from around the world. I just noticed someone was saying they're from Middlesbrough. That's just down the road from the town I grew up in. So hello, Olia, and hello to everyone else. All right, so we're talking about experimentation today and experiment tracking. And while we often think of experiments as being a thing that only scientists do, actually every business needs to perform experiments too. And a common example of this is A/B tests for improving websites and for improving products. And just as a consequence of this ubiquity of the A/B test, more or less every data scientist needs to have at least some understanding of experimentation. And an extra complication is that once an organization is running lots of different experiments, it can become tricky to manage them. And if you can't manage your experiments, you're going to get the wrong answer. They're going to get confused, and that's just a disastrous situation where your data science is all nonsense. So today we're going to learn about experiment tracking. And our guest is Jinan Setpal. He's a machine learning engineer at DagsHub. And Jinan has worked extensively on challenges in natural language processing and more recently machine interpretability. And at DagsHub, his work involves making it easier for everyone to systematically develop and iterate on their MLOps projects. So I'm going to hand it over to you, Jinan. Take it away, please.
Awesome. Thank you, Riz. Thank you, Rishi. That was awesome. And I think Rishi started off by summarizing the entire challenge with data science in general and experiment tracking very, very beautifully. The primary goal within every single organization's data science team is to ensure that everything that they work on is managed and can easily be accessed by someone with no experience in programming. You should not have to open up a terminal window to get started with tracking your experiments or identifying something new or something different. So MLflow, it does a fantastic job in enabling that, and I am super excited to take you all through that entire journey from zero to get started with tracking experiments using MLflow today. So just to get started, can everybody see my screen? Yes or no? All right. Cool. So awesome. Thank you. And this is the Colab notebook that we're going to be using today, and basically getting started with everything. So I believe that the link has been posted in on the chat as well. So if you would like to follow along, please do so. They will be using DagsHub for a part of this workshop because it provides a remote host for MLflow, and we will cover that today. But to get started, MLflow, we integrated MLflow into DagsHub almost 2 years ago now. And we provide a zero configuration MLflow remote with built-in access controls like MLflow's tracking, registry, and deployment functionalities. We have handled many of its specifics and have managed to ease that process as much as possible. So we are hoping to help you guys also leverage the zero configuration functionality of the MLflow server. So here's what we will talk about today. First, we will discuss about why we need MLflow, what MLflow fundamentally is, and then we begin deep diving into their tracking functionality. We understand their nomenclature for runs and experiments, logging runs and experiments, so actually doing the practical logging of the experiments and the runs, and understanding how and where runs are recorded. Finally, we go hands-on with using MLflow with a sample project that we've adapted, and hopefully you guys will also like to follow along through that. So to get started with why we really need MLflow, there are these three memes that illustrate the idea really nicely. So data cleaning is a significant part of machine learning today, especially with large language models. There was this paper called Lima, which is less is more for model alignment, and they used 1,000 fantastic data samples and were able to perform at a level that was at par with GPT-4 on the task that they aligned their language model to. So mastering data cleaning is a massive part of the machine learning process. So the effort and the time that is spent towards things like this is often very, very underestimated. And doing things like hyperparameter tuning manually is a major challenge because it means that you would have to redo a bunch of times in order to identify what hyperparameters work well. And if you are trying to simultaneously optimize a bunch of parameters, that makes the challenge exponentially harder. And before I used MLflow, and before I really knew about MLflow, my colleague used this sort of Notion table to keep track of all of the experiments that they conducted. So this is a table that contains research logs. There are details about the experiment, stuff like parameters, batch size, the epoch, then the status of the experiments, information about the data set, the outcome, and just general comments. Finally, there's also a log file that contains all the repository that you would need. So that's the general idea with regards to the experiment. However, you can pretty easily identify that why Notion is a fantastic tool for just keeping random nodes. But when those nodes become highly numeric in nature and require you to perform a lot of queries over them, it becomes significantly harder to be able to use it at scale. And one way to look at MLflow is like a Notion for machine learning experiments. It is an open source tool that to manage the entire machine learning lifecycle. It supports the live logging of parameters, metrics, metadata, and artifacts when you run any machine learning experiment. And to manage the post-training stage, it also has a model registry with a deployment functionality to custom serve tools. We will be covering the live logging functionality part of MLflow. It was created to reduce the complexity in monitoring experiments, ease the reproducibility of results, which today is especially important because results conducted badly can have lasting consequences on huge populations depending on the impact of the machine learning model. And finally, it also caters to a need of standardization for registering and deploying models into production. So here's a little bit about the organizations that use and contribute to MLflow. The really cool thing about this or about MLflow in general is the fact that it is open source. And what that means is that all organizations can contribute and use it completely freely. And initially, a lot of companies developed their own tools for model and experiment tracking just because it was so important. But all of these developing it themselves was no match for the community. And when Databricks introduced it, it was it basically was adopted by a lot of them. They themselves ended up contributing to it, which makes it even better. And that's kind of the I don't know. I love open source, and I'm super happy that they're successful because of that. So there's that. MLflow has a couple of components. The first one is MLflow tracking, which is the logging of parameters, metrics, and artifacts. MLflow projects, which is packaging and reusing data science code. The MLflow registry, which manages the lifespan of a model, so taking it from the experimentation stage to deployment to finally retiring it once you develop a new state-of-the-art model. And MLflow models, which is just packaging and actually deploying MLflow models that are deemed to be in production. So let's get started with the MLflow tracking functionality. There are runs and experiments, and these are two very important components within MLflow. The experiment unit in MLflow can be considered as a project or an approach. For example, hyperparameter tuning the learning rate of the model. This term is kind of an umbrella term and houses multiple runs in, and you can house multiple runs in a single experiment. So, for instance, if we were looking at optimizing the learning rate of the model, we could say that we have one run with a learning rate of 10 to the power -5 all the way to 1, and we basically compare and see how the model is trained with each of the supplied learning rates. And more than one run may be associated with a single experiment, and each run, like the individual run itself, is a single execution of your data science code, and that records the following information. It records the source of the execution, so it contains the commit hash if your code is tracked via Git, and the original line of code that was utilized for the run. So if you use Python train.py or Python source/train.py, that will also be logged within the run. It also logs artifacts. These are output files that are recorded towards the run. So if you're running an evaluation stage, the images that you generate that have maybe the graphs that show how well the model performs on unseen data, that could be an artifact. The actual model data itself could be another artifact. Parameters, these are stored in the key value format, and they are basic, they're the hyperparameters that are used in the run. So learning rate is one of them. The type of loss function that you use could be another, and so on and so forth. Finally, there are metrics. These are used for evaluation, like root mean square error or ROCE. These are recorded through the extent of a run. So epochs, so every single epoch itself also counts as a metric. And it's basically any data that updates through the extent of a run, while parameters are data that do not update through the extent of a run. So if you have a variable learning rate, that would become a metric, not a parameter. All right. So that's the runs and experiments, and I hope that makes perfect sense. And if it doesn't, please shoot questions in the chat, and either Riz or Rishi would let me know, and we can resolve that as soon as possible. So there is that. Next, we will talk about how and where runs are recorded by MLflow. So MLflow runs can be stored locally in files, either remotely in a tracking server or inside a database that is compatible with SQL Alchemy. That is an open source SQL toolkit and object relational mapper for Python. So the first scenario, or the default scenario, that MLflow uses in order to set up its runs or experiments or both is the completely on localhost scenario. What it does is it creates a directory called ML runs inside your local system as soon as MLflow logs a run or an artifact. Then you are able to view the artifacts using the MLflow UI command. It will bring up a web page, and you can browse all of the experiments along with the graphs through that. It's a good starter mechanism where everything is handled completely locally. However, it performs it gives several restrictions on the actual collaborative aspect of the experiment tracking. So if someone wants to look at the experiments that we have conducted, it becomes extremely hard because it only exists locally inside your repository. And this also cannot be tracked via Git because artifacts generally are significant in size. So you would probably want to use another versioning tool for that, and that complexity scales up very quickly. The UI itself contains the following features. It has experiment-based run listing as well as comparison. You can search for runs by parameter or metric value. You can visualize run metrics, and finally download results from the run as well. The next scenario is MLflow on localhost with SQLite. So the only difference between this and the previous one, where it stores stuff on localhost, and it still is on localhost, it's just that it is using a SQL database instead of just your file system. So it is a little bit more efficient in terms of the way it stores the data. The next scenario is MLflow on localhost using a tracking server. This scenario, again, is pretty similar to the first scenario, but over here, you set up a remote server using MLflow server, and that starts a tracking server at port 5000. And this tracking server is continuously listening to any HTTP request that it gets in order to log experiments. So everything is basically proxied through that. Now, the next scenario is MLflow with a remote tracking server, a backend, as well as artifact stores. So the tracking server backend store and artifact stores are all located on different hosts in distributed architectures, so it is the most efficient possible. I'm just going to make this screen a little bit smaller so everything fits into the single image. But the setup is as follows, right? This diagram describes it pretty well. We have your local host that actually runs all of the code. You have a remote host that is a tracking server, so you can have a separate tracking server that unifies with all of the projects that are running at a simultaneously within your organization. You can have a separate S3 bucket for actually storing artifacts, as well as a PostgreSQL server to actually query any of the metrics that you are using. So this allows you to perform a lot of very, very efficient optimization routines as well. So for instance, your images or artifacts, generally, if you store it into a remote host, that is much better than storing it through SQLite or any SQL server in general. It is a distributed architecture, which means you can scale different components differentiably depending on the actual requirement that you have at hand. And the one caveat with this is the fact that it requires you to set up it requires you to set all of these up differently and link them as well. This also means that you will require to have some DevOps knowledge beforehand. Additionally, since both of the S3 and HTTP requests are sent through the single localhost client, it also requires that entire setup to be done client side as well. So there is the caveat, two caveats of this scenario. So scenario 5 is the MLflow tracking server enabled with a proxied artifact storage. So in this case, we eliminate the need for directly making S3 requests to the remote host, and instead proxy everything through the HTTP server. Wherein if we are using or sending models, images, configs, anything that is to be sent through S3, it is proxied through the HTTP host, and the remote host itself manages the S3 deployment. So this eliminates the second caveat. However, it still does maintain the first one, wherein DevOps knowledge is required in order to use MLflow. That's the best performing scenario that we have, that MLflow provides so far, because it is the most scalable and works well as well. So it is the most efficient. So removing that last caveat from what we have is the scenario 6, which is MLflow x DagsHub. So going through all of this could be a bit of a hassle, even for people who do have a DevOps background. To simplify this, DagsHub decided to do all of the MLOps heavy lifting for you. We provide a free MLflow server with every single repository. You can log your experiments with MLflow to it, view all of its information under the experiment tab, and manage your trained models from the full-fledged MLflow UI built into your DagsHub project. So you can access MLflow as though you were setting it up locally through our client. When you create a repository on DagsHub, a remote MLflow server is automatically created and configured with the project. The repository's MLflow tracking server will be located at the DagsHub Git repo, and you just add .mlflow. So similar to how you would identify a Git host with the .git added to the URL, you would simply add .mlflow, and that gives you the MLflow remote. So that sums it up for the theoretical portion. Now we can deep dive into the actual programming part of this. So that's fantastic. And at this time, if there are any questions, I'd love to take it. And if not, I guess I hope you all have your notebooks up and running. And yeah, we can start off with the hands-on part.
Yeah, not many questions yet. If you do have any questions for Jinan, please do ask them in the chat now. Otherwise, I think we're probably okay to get started.
Fantastic. Okay. Sweet. So to get hands-on, let's start off by forking this project by Eric Levinson. He trains a neural network to classify images as either Mario or Wario. So I forked that and trimmed it, made it, just optimized it a little bit for the purpose of this workshop. And if you press down that URL, you will be redirected to the Mario versus Wario Git repository. So from there, just fork that to your own personal account. You can rename it if you like, but I will just keep it the same. And from there, you should be good to actually start working on the integrating MLflow into an actual project yourself. So I'll wait for this to process. And in the meantime, I will install DagsHub's client repositories and add my information. So feel free to do the same for yours as well. You would want to add your DagsHub username over here and the email that you use to sign up with DagsHub over here. And the DagsHub repo, if you changed it, you could change it. If you didn't, keep that the same. Once that is done, we'll generate an OAuth token for improved account security. And fantastic! It did not request me to authorize it separately, but you should get a link over here which you press and to redirect you to a DagsHub page. Once you press authorize, that should set it up for you. Fantastic. Next, we have this actual repository that is the base repository on which we were going to be working on. Now that we have that in our DagsHub remote, I'm also going to clone that locally. So I will run, I will first configure git and then clone that repository. Oh, I already have the repo clone. Okay, fantastic. So that is that. Once that is done, we can actually install MLflow, which is what we are here to work on. So we have two flavors that MLflow provides. The first is the default one, and the second is MLflow Skinny. So it reduces the set of dependencies that MLflow uses and cuts down also on a couple of features. But it is good for training on an edge device. So for now, we are not on an edge device because Colab provides us with a lot of hefty compute and a nice GPU. So I'll just install the default version of MLflow for now. All right, fantastic. Next, we'll explore the actual project itself. So let's actually understand what's going on before we just start executing random code. We have a couple of stages over here. So there is a data stage or this data folder where we have all of the data for our experiments. There is a configuration file as well as a training file that are both fed as inputs to this training stage. And this training stage runs the Python 3 source /train.py and generates out our models for us. Looking at the data that we have very quickly, let's just take a quick look at what we are actually working with here. So the images are taken from a video game, and they are completely in black and white. Hopefully this opens soon. I'm not having the best internet today. All right. So in the meantime, let's just run the train.py because that was the pivotal script that generated the code. File system is already mounted. Oh, it's running installers again. All right, just a second. If you run into this, which I do not think you will, you would just need to remove the, okay, where is this at? Train.py line 86. There we go. I will just comment this out. So this is for the file system streaming to ensure that we don't have to pull all of the data from the remote again. So once I remove that, that should work just fine. And it begins the actual training process. So this managed to load. We have two distinct folders, one for Mario and the other for Wario. And they each contain images of the or screenshots from the video game. If that ever opens up, I will make sure to show you guys as well. So we completed our training. It's a binary classification task. So we basically want to find or identify if a single image contains Mario or Wario. So we have all of these images, and I will pick one at random and hope that looks soon. But yeah, so the training completed, we ran only 5 epochs and we have an accuracy of 0.64%. So that's not fantastic, given, again, it's a binary classification task. So even if we guessed at random, we would get about 50, but that's fine for now. Now, let us sort of work or begin to integrate MLflow to this project that we have. The first is logging experiments locally, right? So in order to do that, we start off by actually importing MLflow into train.py. So I will open train.py and remove that for space and actually import MLflow in here. And in order to create an experiment, I need to use this command from the command. If I'm using the MLflow CLI. But if I'm using Python, I can use mlflow.createExperiment and give it a name. So I created the simple helper folder or the simple helper file that gets an experiment ID. We basically give it a name as the input, and it gets experiment by name. If from the MLflow either present in localhost or the remote. And if it does not exist, then we receive none. And if it is none, we want to create a new experiment and return the ID. And if it does exist, we just want to return the experiment ID. And that's basically running right here. So if I run this very quickly, I will get 0. That is the new experiment ID that I have gotten from the creation process. Next, I can allocate a run to this actual experiment itself. So if you remember from before, the experiment is the large umbrella that contains all of the runs within it. If we want to add a run to a single umbrella experiment, we want to use this API function where we just provide the experiment ID right here. This experiment ID is what we have gotten from this function. So in order to start an MLflow run, we use the MLflow.startRun Python API call, and we paste this into our train.py with the experiment ID that we obtained from the last execution. And importantly, we need to provide a context to the MLflow start run, so you would not be able to run it outside, or you should run it with the block for context. Finally, let's discuss about how we can actually log information. I'll cut this out and add it back again once we need to actually input stuff. But yeah, here is how we start or actually log information into MLflow. We will first import MLflow to our notebook or by file. Then we use manual logging commands to log all of the features that we discussed earlier. So parameters, metrics, artifacts, and just general text. So for a single parameter, we set up log_param or user log_param and provide a key value pair, and it logs that to the relevant run. If we want to log multiple parameters in one shot, we need to provide a dictionary of key value pairs, and that will give us the final set of parameters in one go. For metrics, it is much of the same. We provide a key as well as a value pair. We also optionally provide the step argument, which is basically the point on the x-axis for the graph itself. So if you have 10 epochs, your first epoch will be step 1, and so on and so forth. For multiple experiments, it is much of the same. You will provide a dictionary of key value pairs and optionally a step keyword argument for the position on the x-axis. Next, we have artifacts. So you could log a single artifact by setting the local path of the artifact itself. And for text, you can use the log text functionality, provide a string of information that you want to include and a local path for a string. This is the actual file or the text file that is generated, and the text is stored into that text file. So that is the basic logging capabilities. MLflow has a bunch of others, and if you would like to read more, please refer to MLflow's tracking docs. Recently, they also started experimenting with LLM and prompt, like tracking stuff for prompts. So that might be something to check out for the future as well. So all of the MLflow code in the section should be under the context block, as I mentioned earlier. But this contains the actual process of logging all of our things. So I'm going to go ahead and copy all of this very quickly and go into train. And before that, actually, I will import from source, what was it? Get or create. Experiment. I think it was the get experiment ID function. All right. So I will log this helper function as well. And let me expand this a little bit and go down to the actual training part of it. So this is the driver for the code itself. We have a get dataset function that gives us all of the data sets and creates data loaders out of it. It is with a batch size of 22 and a validation ratio that I cannot see. It's 0.2. So that is that. We have a get model function, and that gives us the model itself. We then fit the model on our training data, compare it against our validation data for 5 epochs, And then we set up the evaluation part of things where we evaluate it on our test set, get the loss as well as the accuracy, and report none of those actually, and print the final model. So that is that. We have it is printed during the model.evaluate part. So that's that. All right, I stand corrected. Anyways, here is the actual code for the logging of the experiment. So I am going to use the start run functionality for experiment ID. I'm going to call the get experiment ID function from the from this Python file, and provided the name. So over here it's Mario_Vario. Fantastic. And with colon paste. Sorry, I will return it back to the normal size in a second. All right, that, and paste that right here. Make the text visible. All right, there we go. Okay, now from here, all I will do is make sure to align this properly. And that should set up all of our logging. Here, this sets up our actual parameters and the metrics. Metrics we actually do not have at this time. So I will move this entire bit to the bottom for after we complete our training as well as evaluation. Sorry, just a second. I do not see the evaluation code. I'm just going to reset it. Very, very sorry, but source. I think I messed something up. Yeah, okay, there we go. I did actually remove that. So this is here, and I need to perform the imports again. Oh, no, I made the same mistake as earlier. All right, awesome. Now fix this and fix imports. All right, that done. I will run train.py. Oh, I need to comment it out. I forgot that.
Could you just give us a quick summary of what you updated there, just so everyone's clear on what's happening?
Oh, absolutely. I'm sorry. So getting back from start, from like the beginning, right? We imported MLflow to actually use the package and imported the get experiment ID function from source/getter_create_experiment_id.py. Right, this is what we had used initially to get the ID of the experiment that we need in order to define which run do we where the run actually goes. So which experiment does the run actually go to? So from there, we set up the entire training process that we already had from before and start the logging part of things, right? So we use the start run Python function, get experiment ID, and we get Vario's experiment ID. Then we log all of the parameters. So we have the single parameter logging, the multiple parameter logging, the single metric logging, and the multiple metric logging. Then we also log the artifacts. So the artifact is what we got after the model save is complete. And I realize I need to put this up here as well. So we have this, and now everything should work in the correct order. We have the image size, the learning rate as well as the epochs that we are logging. We log the test set loss and also the test set accuracy right here within our metrics section. Next, we log the artifacts and the general text, so general information about the run, and we save it in run_info.txt. So that's the general set of changes that we made. It is exactly the same as this under the with context block at the end of the entire train.py script. So that is the extent of the changes. I'm sorry about being confusing there. So now if we run source.py, we should be able to train everything as before. But now, in addition to just training it, we should also be able to see the result of our experiments that we tracked within the 0 directory under ML runs. So that contains all of the actual information about our training run. So assuming the experiment ID did not update in the last 2 times, we should be able to refresh this once the training run is complete and identify all of the logs and everything that we have actually identified or actually logged using MLflow. So it will follow the structure that we have over here. We have the run hash that we get from the model run. Then this is within the actual experiment ID. Within that, we have the artifacts, so models as well as the run information, the general info that we included, the metrics, test set accuracy, test set loss, epochs, image size, learning rate, everything that we had included from before, and tags, which is metadata about the actual run itself. So the head of the command that was used in order to track the experiment, the source, the experiment name, type, and the user that tracked the experiment. So this says that it is done. I will refresh it real quick and check for the updates. Okay. What happens if I run get experiment ID for this? All right, I'm not sure why I can't see that, but I'll move forward for now. So that is that. Now, this basically saves all of our data locally, but in order to avoid the process of setting up the remote server, we will use DagsHub's integration with MLflow. When you create a repository on DagsHub, a remote MLflow server is automatically created and configured with the project. The tracking server is located at the URL. This is the same as we mentioned above. And in order to actually set it with our machine, all we need to do is configure set tracking URI function within MLflow and give it the remote host that we had mentioned earlier. We can set up our credentials as OS variables, and just like that, we are ready to start actually logging experiments to a remote host. So setting up the environment variable, all I need to do is use execute this cell. We set our tracking username as the DagsHub username, the password as the DagsHub token that we obtained during the OAuth process, and the MLflow tracking URI. Normally, it is not recommended to set the tracking URI as an environment variable simply because it is changes from project to project. However, since it's just one project on our notebook, that's not a problem. So from there, let's update the get or create experiment.py folder in order to actually integrate remote experimentation. So first, I'm going to import OS because we want to get the OS variable for MLflow tracking URI, and copy this line of code that will actually set the tracking URI. Right? It's the Python function which we provide as input the remote URI that we got via DagsHub. Now, once we run this, we can go to our actual DagsHub page and open the experiment section. And this experiment section should now contain or be populated with a single experiment that is completely empty and contains no information. So let's check that out. Oh, I guess that our experiment from earlier was actually logged to the MLflow remote. But yeah, I will check that out. That kind of explains why it was not present locally. All right. Anyways, so that sets up a default experiment. Since the experiment already existed, we do not see anything blank, and we actually saw the populated version of a set experiment. Let me see if I can, yeah, break this. Now it should be empty. And from there, I should be able to run this again. And hopefully we should get an empty MLflow experiment. Yep. Okay. So that is that. And in order to actually begin logging our experiment to the remote host, like we saw earlier, all we need to do is go to train.py and do the exact same thing that we did earlier, wherein we, where is this? Create experiment. We take the set tracking URI code and paste it within the runner for the script, and now it will log all of those metrics that we had earlier into the MLflow remote that is present on the DagsHub end, with all of the I need to report OS, with all of the added functionality and optimizations for performing machine learning experiments both collaboratively and at scale. So I will do that. Run source/train.py, and it should get started. I don't expect the training to improve, but we should be able to do it reproducibly. So that is our plus point. Now, final epoch, we're still at 60% validation accuracy. Okay. I did not expect. Like I said, I expected it to not get better. I did not expect it to get worse, but unfortunately, it did. Anyways, our test accuracy that we report is 0.55, which is a tad over rolling a dice. So it's okay. I will still take it. But if we go to our MLflow remote and refresh this very quickly, we should be able to identify the MLflow experiment within this. Within this remote. Right, awesome. So that is our actual run. We identify the fact that we do not get a fantastic test accuracy, but that is okay. So now we have covered the basic general understanding of sort of setting up the logging portion of an experiment as well as logging it remotely. But there is still one very important concern. What if I forget something? So if you're a forgetful human logger like I am, I tend to forget a lot of information that I added and is relevant for the training run itself, but I just do not fail to log it at the time. And I'm also lazy, so I don't know what to set it up manually. MLflow basically has set up this auto logging functionality where you can do all of the parameter logging automatically and not have to worry about it. So it exists for a lot of frameworks like scikit-learn, TensorFlow and Keras, Gluon, XGBoost, LightGBM, StatsModel, Spark, FastAI, PyTorch. It's basically everything that you would need. You can use MLflow.autolog functionality in by itself to enable logging for all of the supported libraries. However, it is still better to specify the library manually. And for now, we are going to stick with that because it is a lot less volatile. So I'll add MLflow.tensorflow.autolog because we are using TensorFlow for this project right above the with start run call and rerun all of our code in order to see the log metrics. So I will do that very quickly. I will go to train.py. I will remove all of the manual logging that we have set up. So we can like objectively compare the importance or the difference between logging manually and logging automatically. I will set the width call just before model.fit and add or and indent this by 1. Once I do that, I will use MLflow.tensorflow.autolog and save this. And that is all of the autologgable configuration done. Right now, on top of this, if you do find there are some features that are not set up or identified by MLflow, you can manually go ahead and set that up and it will do it for you. So I save this just to be sure, and I will run this same training script one more time, and hopefully it should not give us any issues. There are warnings, but warnings are not errors, so it is no problem. And that is training. While that happens, I also wanted to mention something. MLflow also places a focus on reproducibility of experiments, and with every single run, it actually identifies the hash that was used in order to run the code. So this commit ID is basically just a piece of the information that was logged. So you know what your code was or at the time of running. So if you update the code, like create an additional loss function or something, you can specifically configure that into your code or know that it was that specific thing that or that specific loss function that you added that caused the divergent behavior, right? So that is also a very, very important reason to git commit as much as possible, and ideally with every single run whenever anything is changed between runs. So that is done. I am going to refresh this in order to identify the additional experiment that we had logged. And then we can compare those two experiments and see the difference between the logging capabilities that we have. So right off the bat, we can see that there are a lot of things that we already missed. But if I just compare it very quickly, that extent becomes all the more obvious. All receptive do 208 is the information that we had, and enthused grub is the information that Autolog set up. So we have this. There is image size and learning rate that they actually missed. I think LR is mentioned somewhere up top, but I'll have to check that. In either case, if we find this information missing that we do want, we can definitely add that manually, and that will also fall within the same run, provided it is within that context window. So we can also see some visualizations for the accuracy of the model, the loss of the model, how well it worked. And if we had two experiments that ran with all of this data, it would also overlay it on the singular graph. So you would be able to compare that manually as well. So the images that we actually trained on finally decided to load up. Here are the Mario images, and here is the Wario image. Wario looks way more menacing than that. Anyways, there is that. And now that we are done with this, I will commit and push the MLflow, the changes that I have made to my repository, and I should be able to check that as well in our actual Git part of the DagsHub repository. And that is it. Congratulations. You can now integrate MLflow's experiment tracking into all of your projects. So that's all that I have for today. I hope you had a good time and were able to learn a little something. And if there are any questions at this time, I would be very happy to take them.
Brilliant. We've got a couple of questions from the audience. We'll get to those in a moment. So thank you very much, Gina. That was really informative, like very cool sort of workflow there. Before we get to audience questions, I just want to say we've got a few upcoming webinars that you may want to attend. So tomorrow we've got people from Specsavers, the opticians, talking about how they use data in their company and how they've been making use of DataCamp. On Friday, we've got a training on using the ChatGPT code interpreter for data science. And then next Tuesday, there is a session on building AI skills with DataCamp. So please do sign up for those at datacamp.com/webinars. Gina, I also have a question for you. So a lot of the stuff you're doing today involves quite a lot of code. And when you're running experiments, there are often a lot of non-technical stakeholders involved. So for example, like product managers probably want to see how their experiments perform and things like that. So can you just talk a bit about how non-technical people can make use of the tracking features that you've been talking about today?
Yes, absolutely. So if I can go back to my screen, we can basically set up the DagsHub repository. Now over here, this is your repository and it is hosted by DagsHub. So this is present on the cloud. You would, in order to add someone like a project manager or anyone on your team that wants to access these experiments, they can simply access this through the link. If it is private, you can add them as a collaborator and they will be able to see it. And from there, they can open up the experiments tab, and through the experiments tab they are able to pick out an experiment. For instance, let's say this one, and if they want to identify I don't know, test accuracy for the last 3 epochs, they can do so by just setting up the filter for here, and then they can make that identification. So if there were a lot more experiments over here, they could work on it themselves and compare all of the experiments for themselves and identify which one works best. And accordingly, they could also use the MLflow UI that is present directly in DagsHub. So I'll pull that up as well in a moment. But this relates to the model registry component as well. So for someone who is maybe on the DevOps side of things, or like the front end or project management side of things, who wouldn't want to really worry about all of the experiments, but would want to know which is the model that they want to pick up for actually deploying it, they could use the MLflow registry part of things and open the actual integrated MLflow UI. Then within models, they could pick out the model which we haven't logged, and we will cover that within our model registry part of things, and set it up with a production stage, or move it to a staging to the staging stage, or maybe an R-type stage, whatever is relevant to their problem. And from there, they are able to utilize that UI and basically pick out what is relevant for the management side of things.
Okay, so I mean, you've basically got like a built-in dashboard there that's going to explain like all the metrics you need, and that's auto-generated then, so you don't need to do anything to create that.
Absolutely. As provided that you're using the logging functionality, everything from there is auto-generated.
Super. And just to provide a bit more motivation, can you talk a bit about like what are the most common problems if you aren't tracking experiments properly? Like, what are the common things that goes wrong?
Yeah, sure, of course. So I am myself, I'm pretty recent to using MLflow and stuff for experiment tracking. And before this, I used to just completely use Jupyter notebooks for all of my experiments because they work so well. But one challenge with Jupyter notebooks is the fact that their execution order is not sequential, right? And if you are working on a challenge, you do not want to be thinking about the fact that about the execution order of your notebook. And you may work on it for like, say, a couple of hours, save your project, and the next day you open it up and the execution order is not the same. So you have multiple locations where you have defined the similar variables. You don't know which variable actually accounted for the run. You don't know which one actually gave you the result that you wanted. And now you have to run those two things again or guess. And neither of those are ideal for science, right? Science needs to be as non-guessable as possible. You have to be as sure as you possibly can. So MLflow allows you to be as sure as you possibly can without having to take the tedious effort of making sure that everything works or is logged or can be ran sequentially. So that's really cool about it.
Thank you. And just one last question from me before we go to audience questions. I've often a company's going to run lots of fairly similar experiments. Like, think about it's going to be a dozen experiments going on a landing page. So is it possible to reuse code from one experiment to the next? How do you go about recycling things?
Absolutely. So suppose you were to say, the one example that I gave from the actual workshop was the fact that you maybe want to change or test the learning rate of the model, and that would be one experiment. So suppose you were to change that and say, I would like to test the epsilon that I'm using within added in order to see how well that model performs. what you could do is keep all of the code basically exactly the same. You would open up train.py, and over here you would basically set up a for loop that iterates through a series of epsilons. And this experiment, you would change it to say, I don't know, epsilon optimization, and that will now change that experiment completely, and you can test which epsilon works best for your specific purpose, and that becomes the completely different. So you can reuse a large part of your code. The primary thing that you would have to change is your driver code, and that's about it.
Okay, so if you're running very similar experiments, pretty straightforward to reuse a lot of your work. Excellent.
Absolutely.
All right, let's get on to some audience questions. First one is actually, it's a request from Wallace saying, because you made some changes to the notebook during the session, can you just make sure those are updated? So if you want to reuse your work, then they can do.
Absolutely. So I'll just save this right away and make sure that if you refresh the original link, that should work right off the bat. I didn't. The only main change that I made to the actual notebook was actually checking out the original training.py code. So I accidentally erased the model, evaluating the model parts of this code, and in order to get it back, I changed that part of it. But besides that, nothing actually is different. If you want to see the difference within the actual integration part of MLflow, the commit that I pushed should have that information there. So that is not the default repository. I can type the link over here or post it in the chat, whichever is more convenient. But yeah, it is this link that has all of the code or all of the updated code with the integration already ready.
Perfect, thank you. And a question from Alex saying, how big was the training data that you were using in the example?
How big was the training data? Let's find out, I guess. Uh, 4 megabytes. Not a lot. Yeah, it's 4 megabytes.
Ah, very good. Okay, so we've got time for 2 or 3 more questions. So this one comes from an anonymous LinkedIn user saying, how can you save a custom Python model, not scikit-learn or PyTorch, using logging with all dependencies?
Okay. Right, awesome. So that is actually pretty awesome part of what MLflow allows. So MLflow has this thing called the model registry that I touched a little bit on throughout this session. But the basic idea with it is that one of the functionalities that the MLflow model registry has is that it allows you to pick or create a custom PyFunc class within MLflow and integrate that reproducibly. So you would set up the init function of the class with all of the dependencies, so loading anything or importing any modules, and loading up the data and running the inference code. So that one function itself. And that would allow you to save or run a custom Python model with that has already been logged and registered. For actually logging and initially registering the model, as long as you're saving it to a local directory, you can use the save dir functionality and save that directory into the MLflow run or log it to the MLflow run. And one thing to note, with things like wheel, saving a custom wheel, you can host that on a Git repository or something, and pip can manually install it. So within your requirements.txt file, you can just set up a Git plus HTTPS and the URL of the Git repo that has the Python wheel file, and it will install it from there. So that would probably work.
Nice. Okay. And we're sort of at time. There's 2 more interesting questions I want to go through. So if we do these quickly. So one of these is for Wallace again. So Wallace is asking, what happens if you're running multiple experiments at the same time? How does that affect the tracking?
So that's each run creates a specific hash. So if you are using something like Ray that runs multiple, that performs hyperparameter optimization in parallel by default, it will not affect it in any way because it will create a specific hash for each run and log all of the data to that hash within your MLflow remote or Localhost, depending on what scenario you're using. So it will work completely fine in parallel as well. So you can run parallel runs in simultaneously and find out what works best much quicker than just doing everything sequentially.
Okay, that's good to know that you can run multiple experiments at once. And final question, another anonymous LinkedIn user. So this is, you covered using MLflow, you covered using DagsHub. So can you just explain
Okay.
where the
Yeah.
similarity, where the overlapping functionality ends?
Awesome. So the thing is, I wouldn't say DagsHub versus MLflow, right? It's DagsHub and MLflow. They're effectively we integrate MLflow completely inherently. So it is not us versus them; it is us and them. MLflow requires you to set up, if you want to set it up scalably for either your own projects or for an organization. It requires you to perform a lot of DevOps beforehand, right? For instance, Alchemy and the PostgreSQL server, all of these components sort of have to work together. And if something breaks, you will have to fix that, and your setup will not work correctly until you fix that. So that can either be managed by a DevOps personnel that is sort of working to ensure that nothing goes wrong, or you could create a repository on DagsHub, and we will make sure that that is not a problem at all for you. So it's just optimizing the MLflow process. Besides that, it is entirely similar as just using MLflow yourself.
All right, super. That's good to know. And it just seemed like it's a pretty powerful combination, the two tools together. Excellent. Okay, so thank you once again, Jen. That was a really cool session. Very powerful, advanced stuff being shown there. So I hope it's something our attendees can try out for themselves. Thank you to Reese for moderating. Thank you to everyone who asked a question. Thank you to everyone who showed up today. And I hope to see you again in future webinars.
Thank you.